Functions are essential in a data science project because they make the code more modular, reusable, and testable. However, writing a messy function that tries to do too much can introduce maintenance hurdles. Consider the following code, which imputes missing values. The function is lengthy, complex, and attempts to perform multiple tasks. Unfortunately, functions like this are common in a data science project. In this video, we will refactor this function using the following steps. Remove redundant code. Split the function into smaller units. Remove duplicates. Make code extendable without alteration. And strengthen code against invalid data inputs. Let's start with removing redundant code. The first problem with this code is that each column is set to missing individually. To address this issue, let's group columns that are labeled missing and fill them using loops. The second problem is that it loops through every column to fill numbers with 0, which is inefficient. To make this code more efficient, batch impute columns with 0 using pandas fill NA. The next step in refactoring the code is to split the function into smaller units. The impute missing values function performs various data cleaning operations, including filling missing values with group statistics, filling missing values with constants, and filling missing values with the most frequent value. The combination of tasks can make testing challenging, as it requires a diverse range of data samples covering multiple columns with various values. To address this, we will break this function down into smaller functions, each handling a specific type of missing data. The impute missing values with group statistic function fills missing values in a target feature by applying the most common value, median, or mean of each group determined by another feature in the data frame. The impute missing values with constant function fills missing values in specified features with a provided constant value. The impute missing values with statistics function fills missing values in specified features with the mode, median, or mean of each feature. The impute missing values function will then combine these functions. Now, each imputing function can be tested individually, making the test more concise and easier to understand. The third step in refactoring the code is to remove code duplicates. The two functions impute missing values with group statistic and impute missing values with statistics perform a similar pattern of actions, including checking the value of strategy and applying the corresponding statistical function to fill missing values. If a change or a bug fix is required, it needs to be applied in multiple places. This increases the risk of inconsistencies if the change is not replicated exactly in all instances of the duplicated code. To address these issues, the duplicated logic can be abstracted into a shared function called getStrategy function. This would centralize the imputation logic, making the codebase easier to manage, extend, and test. The fourth step in refactoring the code is to make it extendable without alteration using the open-close principle. The open-close principle suggests that objects should be designed to accommodate new features without changing the existing code that's already been developed and tested. The impute missing values function violates the open-close principle because it requires changes to its code if the data sets or features change. When you make changes to the code, you may need to retest the entire codebase to ensure that the changes did not break anything. This can be time-consuming and may delay the release of the software. To solve this problem, we can define an abstract-based class DataFrameImputer with an abstract method impute. Subsequently, we can create a variety of concrete imputer classes that inherit from DataFrameImputer, such as Group Statistics Imputer, Constant Imputer, and Statistics Imputer. Since all impute classes have the impute method, the impute missing values function can accept a list of DataFrameImputer objects and applies their impute method to the data frame in a loop. By doing so, users can extend the functionalities of the impute missing values function without modifying the underlying code. The last step in refactoring the code is to strengthen it against invalid data inputs. The second half of the robustness principle states, be liberal in what you accept from others. This means that your code should be able to handle inputs that contain unexpected variations. However, the group statistics imputer class violates this principle by not handling cases where the group feature column contains missing values. This results in the impute method not raising an error, but the output still includes the missing values, which differs from user expectations. To address this issue, we will raise a value error if the group feature column contains missing values. This will ensure that the imputed values are consistent with the user's expectations. Now, let's take a look at the impute missing values function. It doesn't handle cases where the value for the imputer's parameter is a single imputer. If users pass an individual imputer instance rather than a list, Python will try to iterate over the object, leading to a type error. To accommodate this, we can use the check variables isList function to turn the imputers into a list if it is not already one. This will allow users to provide a single data from imputer instance as the imputer's argument. In this video, we have transformed a function from this to a more refined version. This new function is scalable and maintainable, allowing for easy integration of new data and methods as needed. Another crucial aspect of developing a scalable function is to ensure its reliability through rigorous testing. In this next video, you will learn how to create tests for your data science project using PyTest.